Okay, hello everyone. Welcome to the next episode of our little course. And in this one, we will introduce and formalize the problem of traffic signal control. Actually, the main goal of traffic signal control is usually to decrease congestion. These would be the traffic jams. And intuitively, congestion occurs when vehicles are moving by two conflicting roads. So in order for one of them to be able to pass, the other has to be stopped. As we can see here in the picture, the cars going from the north to the south would cross with the cars going from the east to the west, and so we would need some sort of traffic signal control to allow them to move forward. And in fact, in modern cities, which struggled with congestion the most, we have many such intersections like this one pictured here. And actually, it becomes impossible to deduce a globally optimal solution to how we can control traffic. The system is basically too big and too complex. So we cannot deal with the notion of global optimality, but we can look into notions of local optimality. And then some further nomenclature that will be useful. Here you can see movements. So movements would be basically cars going from one lane to another over an intersection. And this might involve a change of direction, for example, as in the case of going right or left, or no change, as in the case of just going straight through. On the other hand, a phase is a collection of non-conflicting movements. So these would be the movements that we can give green at the same time. So for example, going through from the north and south will never cross. And so that would be the phase 2 in this diagram. And here we omitted right turns in the description of phases. They're usually considered to be non-conflicting, so can be green at any time. And here these movements and these phases actually correspond to all possible movements and phases that we could have on a simple intersection with two roads crossing, such as the one pictured in the previous slide. Okay, and let's talk now a bit about existing methods of traffic signal control. So the simplest method would be fixed scheduling, and in its basic form, it would consist of just a fixed periodic service where we would serve consecutive phases. So for example, from the previous slide, we go phase 1 for, let's say, 20 seconds, and then phase 2 for 20 seconds, phase 3, and so on, until we reach phase 1 again, and continue periodically. This method can also be extended in a data-driven way to adapt to different conditions. So for example, we could imagine having two schedules, one that we would use in congested conditions, so for example, during rush hours, and another one for normal traffic, as we expect these two different scenarios to be slightly different and require different phases perhaps to be activated for longer times or shorter times. Another method would be analytic solutions. So in general, an analytic solution consists of using certain physical models of traffic, where we would try to optimize some measures derived from physics-based theories. However, usually an analytic derivation of a global optimum, as we have already mentioned, will be impossible, but we can still successfully use analytic methods to get some sort of, local optimas. And then we could, imagine optimizing greedily on a local scale, for example, for a single intersection or perhaps for a neighborhood. And then there are also analytic methods which could attempt to optimize in such a way that the interactions between neighbors would be positive. So we would try in that way to maximize positive interactions between individual intersections, and in the hopes of that leading to coordination on the global scale. And then finally, we have this novel popular approach, which is deep reinforcement learning. And it makes a lot of sense here to use deep learning for such a problem, traffic signal control, since it is often a good tool for problems where our analytic knowledge is not enough, so where we cannot really optimize globally. And here we'll briefly explain how reinforcement learning agent, which controls a single intersection in the city, works. So generally, what you need to know is that reinforcement learning relies on three main kind of concepts. The state is the representation of a situation at a given time, the representation of the problem that is to be solved. And in the case of traffic signal control, this can be, for example, the number of vehicles on the lanes, or maybe their speeds, perhaps even a photograph of the intersection that we're controlling. The actions are ways for the agent to interact with its environment. So in that case, we could have, for example, activating different phases. And finally, the reward, which you can see here, is gives agent the information about the situation. So it gives it a sense of whether it's in the good state or a bad state, where it's going well or not going well at all. So here we would probably want the reward to represent, in some sense, the level of congestion around the intersection. Or perhaps it could be, for example, an indicator of like how many cars are waiting at the intersection, or how much the cars are spread around incoming and outgoing lanes. And in one of the flavors of reinforcement learning that we call deep key learning, an RL agent learns basically by taking actions and storing information about these like state, action, reward, state tuples. So basically, we are in a given state, we take an action, and then we see what reward we got and which state we were brought to. And these tuples can be then used to train a new deep neural network. And once it's trained, once it's been presented with enough examples, it can basically predict the expected reward in a given state for each of the possible actions. And then we would just choose actions leading to higher rewards. And the problem here is that the first agent doesn't really know anything, right? Doesn't know what actions are good and bad, and so it does need to explore. And this is often done via just making random decisions at first, but there are also smarter heuristic-based methods. Okay, so thank you very much for your attention. In the last episode, we will see how we can investigate the environmental impact of our algorithms and how to make these algorithms more sustainable without sacrificing efficiency.